Our planet, a blue oasis in the vastness of space, seems deceptively still. From our vantage point, we witness the rising and setting sun, the ebb and flow of tides. But beneath this serene facade, Earth is a world in perpetual motion. Continents drift, oceans swell, and deep within the planet's core, forces beyond our immediate perception are constantly reshaping the very ground beneath our feet. This hidden dynamism manifests itself in many ways, but none so dramatic, so potentially destructive as the phenomenon of fault lines. Fault lines, hidden cracks in Earth's crust, are a testament to the immense power of our planet's internal forces. They mark where tectonic plates meet and clash, often invisible but felt with terrifying force. Understanding fault lines helps us grasp the forces shaping our planet and the risks they pose. These zones of potential rupture snake across continents and plunge beneath the ocean floor. From the Himalayas to the Ring of Fire, they shape our planet's past, present, and future. Our journey into the heart of fault lines begins with plate tectonics. Imagine a time-lapse spanning millions of years. Continents, once a supercontinent, drift apart in a slow, majestic dance. This dance continues today, a testament to our restless planet. What drives this relentless motion? The answer lies in the mantle. Heat from the core creates convection currents. These currents drag tectonic plates, causing them to move. It's a slow drift, reshaping our planet over eons. Imagine Earth's crust not as a single solid shell, but as a mosaic of these massive tectonic plates, each one a jigsaw piece in a constantly shifting global puzzle. These plates, far from being static, interact with each other in a variety of ways. Their boundaries, the zones where Earth's internal forces are most dramatically displayed. It's along these boundaries, these zones of intense geological activity, that the story of fault lines unfolds. There are three main types of plate boundaries: convergent, where plates collide; divergent, where they move apart; and transform, where they slide past each other horizontally. Each type of boundary generates its own unique set of forces, shaping the landscape above in dramatic ways. Convergent boundaries, for example, are often associated with towering mountain ranges like the Himalayas, formed as colliding plates buckle and fold. The unstoppable force. Picture two tectonic plates driven by the relentless forces of mantle convection inexorably converging. As these massive slabs of Earth's crust collide, the pressure builds, creating a zone of unimaginable stress. Rock, seemingly solid and unyielding, begins to deform, bending, buckling, and even melting under the immense pressure. It's a slow-motion collision spanning millions of years, but the forces involved are truly titanic. Think of a vice slowly tightening its grip on a block of wood. At first the wood resists, but as the pressure increases, it begins to creak and groan, eventually splintering and cracking under the strain. Similarly, the immense forces generated by colliding tectonic plates push the rocks at their boundaries to their breaking point. Something has to give. Stress on the rocks. The rocks along plate boundaries experience different types of stress depending on the direction of plate movement. Convergent boundaries where plates collide are characterized by compressional stress, like squeezing a stress ball in your hand. Divergent boundaries where plates move apart experience tensional stress, like pulling on a rubber band. And transform boundaries where plates slide past each other are subjected to shear stress, like spreading a deck of cards. Imagine a wooden plank being bent. As the bending force increases, the top of the plank experiences tension, while the bottom experiences compression. Eventually, the stress becomes too great and the plank snaps, creating a fracture. Similarly, rocks under stress will eventually fracture, creating a break in the Earth's crust, a fault. Birth of a fracture. When the stress on rocks exceeds their strength, they fracture, creating a break in the Earth's crust. This break, initially a small crack, can grow over time, eventually forming a fault. The rocks on either side of the fault are now free to move relative to each other. This movement can be sudden and violent, resulting in an earthquake, or it can be slow and gradual, barely perceptible at the surface. The surface along which the rocks break is called the fault plane. The block of rock above the fault plane is called the hanging wall, while the block below is called the footwall. Understanding these basic components of a fault is crucial to understanding the different types of faults and the hazards they pose. Imagine holding a twig, bending it slowly. As the pressure mounts, you hear a faint creaking, a warning signal. Then snap! The twig breaks, releasing the stored energy. This sudden release is analogous to what happens within the Earth's crust along a fault line. The rocks, under immense stress from the tectonic plates' relentless movement, finally reach their breaking point. The fracture, a seemingly insignificant crack at first, becomes a conduit for the Earth's pent-up energy to escape. This breaking point, this moment of rupture, is when the Earth quite literally moves beneath our feet. The energy released during this rupture travels in waves, radiating outward from the fault line. We experience these waves as earthquakes, the ground shaking, sometimes violently, as the Earth releases the stress built up over countless years. The energy released during an earthquake, traveling in the form of seismic waves, is staggering. These waves, like ripples in a pond, spread out from the fault line at incredible speeds, reaching every corner of the globe. The intensity of these waves, and thus the severity of the earthquake, depends on a multitude of factors, including the amount of stress released, the depth of the earthquake, and the type of fault involved. Scientists use instruments called seismographs to detect and measure these seismic waves, providing valuable data about the earthquake's strength, location, and depth. The study of these waves, known as seismology, has been instrumental in understanding the inner workings of our planet and the forces that shape its surface. Fault lines, despite their depiction in popular culture as single, clean breaks in the Earth's crust, are often far more complex. They are not singular cracks, but rather zones of deformation, networks of interconnected fractures that can extend for miles beneath the surface. These fault systems, rather than being static, are constantly evolving, with new faults forming and existing faults reactivating over time. Imagine a shattered window pane, a web of cracks radiating outward from the point of impact. Similarly, fault zones often consist of a main fault where the largest displacement occurs, accompanied by a network of smaller subsidiary faults. These subsidiary faults, while individually less significant, can still contribute to the overall seismic hazard of a region. Geologists, in their quest to understand these hidden cracks in the Earth's crust, have developed sophisticated techniques for mapping and studying fault lines. These techniques range from traditional field observations, where geologists physically examine rock formations and look for evidence of past earthquakes, to cutting-edge technologies like aerial surveys and ground-penetrating radar, which allow scientists to create detailed images of the subsurface. By mapping the location, orientation, and history of movement along fault lines, geologists can assess the seismic hazard of a region and provide crucial information for earthquake preparedness, infrastructure planning, and disaster mitigation efforts. Perhaps the most infamous fault line in the world, the San Andreas Fault, slices through the California landscape, a stark reminder of the immense forces at play beneath our feet. This continental transform fault, where the Pacific Plate grinds horizontally past the North American Plate, has been responsible for some of the most powerful earthquakes in recorded history. From the devastating San Francisco earthquake of 1906 to the more recent Loma Prieta earthquake of 1989, the San Andreas Fault serves as a constant reminder of the potential for seismic activity along its length. Understanding the San Andreas, and indeed all fault lines, is not just about unraveling the mysteries of our planet's past. It's about preparing for the future and mitigating the risks posed by these powerful forces of nature. Just as there are different ways to tear a piece of fabric, the Earth's crust fractures in various ways depending on the direction of force applied by those restless tectonic plates. Geologists, in their quest to decipher the language of the Earth, have classified these fractures into distinct types, each with its own unique characteristics and implications for the landscape above. These classifications, far from being mere academic exercises, help us understand the forces that shape our planet and the potential hazards they pose. The three main types, normal, reverse, and strike-slip faults, are distinguished by the direction of movement along the fault plane, that invisible surface where the Earth's crust is broken. Each type tells a story of stress, strain, and the relentless interplay of forces deep within our planet. When gravity takes over normal faults. Imagine holding a cloth tautly, then gently pulling the two ends apart. The fabric stretches and tears, creating a gap. Normal faults operate similarly, but on a grander scale. Tensional forces pull tectonic plates apart, stretching and thinning the Earth's crust. Gravity pulls the hanging wall downward relative to the footwall. This creates valleys known as grabens, bounded by horsts. The Basin and Range province showcases the power of normal faulting. These faults can generate significant but often less violent earthquakes. Pushing against the grain reverse faults. If normal faults are about pulling apart, reverse faults are their mirror image, embodying the forces of compression. Picture two tectonic plates colliding head-on, an unstoppable force meeting an immovable object. The immense pressure generated by this collision forces the hanging wall of the fault upward relative to the footwall, defying gravity's relentless pull. This upward movement, like a sculptor molding clay, thrusts rock layers upward, creating towering mountain ranges. The Himalayas, Earth's highest mountain range, stand as a majestic testament to the power of reverse faults. Born from the ongoing collision of the Indian and Eurasian tectonic plates, these mountains continue to rise millimeter by millimeter as the relentless forces of plate tectonics push ever onward. Reverse faults, due to the immense stresses involved, are often associated with the most powerful earthquakes, their ruptures capable of unleashing tremendous energy. Side-by-side strike-slip faults. Imagine placing your hands flat on a table, then sliding them past each other. This horizontal movement is the defining characteristic of strike-slip faults. Unlike normal and reverse faults, strike-slip faults are all about lateral displacement. Their movement often marked by long, linear valleys and offset landforms. The San Andreas Fault is a prime example of a strike-slip fault. The Pacific Plate grinds northward past the North American Plate. This movement has offset geological features by hundreds of kilometers. Strike-slip faults can generate powerful earthquakes. Reading the language of faults. Understanding the different types of faults is not just an academic exercise. It's about deciphering the language of the Earth, reading the stories etched in stone. By studying the orientation, movement, and history of faults, geologists can piece together the tectonic history of a region, understanding the forces that have shaped the landscape and assessing the potential for future earthquakes. This knowledge is crucial for earthquake preparedness, infrastructure planning, and disaster mitigation. By understanding the language of faults, we are better equipped to live with and mitigate the risks posed by these powerful forces that shape our planet. The Earth trembles. Imagine standing on solid ground only to have it lurch beneath your feet. Buildings sway, windows shatter, and a deep roar rises from the Earth. This is the reality of an earthquake caused by the movement of rock masses along a fault line. For millennia, these events were attributed to supernatural forces or divine wrath. Modern geology reveals the science behind these events, linking fault lines to earthquakes. The Earth's crust is in constant flux, with tectonic plates grinding and accumulating stress. This stress builds up over time like a coiled spring until it reaches a breaking point. A chain reaction of energy. When stress exceeds rock strength, they fracture, rupturing the Earth's crust. This releases energy as seismic waves, like ripples from a pebble in water. Seismic waves spread outwards. They travel through the Earth at incredible speeds. Different types of waves have unique characteristics. P waves compress and expand the ground. S waves shake the ground up and down or side to side. Surface waves roll along the Earth's surface. These waves cause the ground to shake, toppling buildings and reshaping landscapes. In the aftermath of an earthquake, the question on everyone's mind is, how strong was it? To answer this question, scientists use a scale to measure the magnitude of an earthquake, quantifying the energy it releases. The most well-known scale, the Richter scale, assigns a numerical value to an earthquake based on the amplitude of seismic waves recorded by seismographs. Each whole number increase on the Richter scale represents a 10-fold increase in wave amplitude and a 32-fold increase in energy release. While the Richter scale is widely recognized, scientists often use other scales, like the moment magnitude scale, which provides a more accurate measure of the energy released in very large earthquakes. Regardless of the scale used, understanding an earthquake's magnitude is crucial for assessing its potential for damage and guiding disaster response efforts. Despite advances in seismology, predicting earthquakes with pinpoint accuracy remains an elusive goal. The Earth's crust, with its complex network of faults and constantly shifting stresses, is a dynamic system. Its behavior influenced by a multitude of factors we are only beginning to understand. While scientists can identify areas at high risk of earthquakes based on historical data and geological mapping, pinpointing the exact time, location, and magnitude of a future earthquake remains beyond our current capabilities. This inherent unpredictability underscores the importance of earthquake preparedness, particularly in regions located along active fault lines. Building codes designed to withstand seismic shaking, early warning systems that provide precious seconds of notice before the shaking starts, and public awareness campaigns that educate communities on how to stay safe during an earthquake. All these measures play a vital role in mitigating the risks posed by these unpredictable events. Living in earthquake-prone regions requires a unique blend of awareness and acceptance. While the threat of earthquakes is ever present, so too is the resilience of the human spirit. We adapt, we prepare, and we rebuild, learning from past experiences to create safer, more resilient communities. Understanding fault lines and the earthquakes they generate is not about living in fear of the Earth's power, but about respecting its dynamism and acknowledging our place within its grand, ever-evolving story. By studying these hidden cracks in the Earth's crust, we gain a deeper appreciation for the forces that shape our planet, and we equip ourselves with the knowledge to live more safely and sustainably in a world where the ground can and will move beneath our feet. As we've journeyed from the depths of the Earth's mantle to the towering heights of mountain ranges, one theme emerges. Our planet is dynamic and ever-evolving. The ground beneath our feet is in a constant state of flux, reshaped by the slow dance of tectonic plates. Fault lines are visible manifestations of this process, a testament to the power beneath our feet. Fault lines, far from being isolated phenomena, are interconnected features of a global tectonic system. The movement along one fault can trigger a chain reaction, influencing stress levels and potentially triggering earthquakes along other faults thousands of kilometers away. Understanding these connections is crucial for assessing seismic hazards and developing effective mitigation strategies. The Earth in its geological entirety is a complex system, its parts interconnected in ways we're only beginning to comprehend. Moreover, the impact of fault lines extends far beyond the immediate vicinity of an earthquake. Tsunamis, those towering ocean waves triggered by undersea earthquakes, can devastate coastal communities thousands of kilometers from the epicenter. Landslides, ground liquefaction, and other secondary effects of earthquakes can also cause widespread damage and disruption. The study of fault lines, therefore, extends far beyond the realm of geology, encompassing fields like oceanography, civil engineering, and urban planning. Knowledge, as the saying goes, is power. Understanding fault lines, their behavior, and the hazards they pose is not about living in fear of the Earth's power, but about empowering ourselves to live more safely and sustainably in a world where earthquakes are an inevitable reality. By educating ourselves and our communities, we can take proactive steps to mitigate the risks and build resilience in the face of these natural disasters. Earthquake preparedness encompasses a wide range of measures, from individual actions like securing heavy objects in our homes and developing family emergency plans, to community-wide efforts like strengthening building codes and establishing early warning systems. By investing in preparedness, we invest in our safety, our resilience, and our ability to recover and rebuild in the aftermath of an earthquake. The Earth will continue to move beneath our feet, but with knowledge and preparation, we can weather the tremors and emerge stronger on the other side.